Thanks for the invitation. And I know it's very rushed after this talk, but I just wanted to remind everyone that Sunday is Mother's Day. And so if you have time, you can go to the Student Center. There's Mother's Day cards that are $1.99. There's a post office that cash in there's an ATM. You can have a quick bite to fit that in. So if you're married to a mother, or have one or something. Anyway, okay. That's right. So I'm going to talk about this. This is partially joined with Somnath, Basu and McGibbon, and Sullivan, and other parts, Sullivan. And I'm going to call this. This is an algebraic topology talk set in the land of low-dimensional topology with some connections to symplectic topology. But I'm not an algebraic topologist, so it's kind of a non-algebraic topologist talking to non-algebraic topologists. So I'll start with the connections anyway, and then we would go from there. Okay, so let me just give a quick overview. What the story I want to talk about. So I'm going to look at, and be very general now, so the overview is very general. So I've got a submanifold in manifold X with pick your favorite hypothesis about this. And then we're going to consider some sort of space of strings. So actually two kinds, open and closed strings, and I'll just use this notation once, omega, which by strings I mean either these are maps from the interval into your manifold such that the endpoints land on your submanifold, or else they're just maps of a set of these things. Maps from S1. Okay, you call these open or closed strings. And what do you do with these things? Well, you look at chains of these maps, families of these maps, and you have, in addition to, and then you use some sort of geometric intersection. Just use intersections of these strings with either themselves or other strings or the submanifold or something to define operations on the homology of the space of strings. Or sometimes you look at some sort of equivariant homology in the space of strings. You can do that. Okay, so for example, what might you try to define? Well, let's say you have you have some submanifold like a knot K, and you have some strings here. So I'll draw another image. You could do some sort of splitting operation and get a 1-to-2 operation. Okay, and this might be called a coproduct because you'll verify that it satisfies some sort of co-associativity. And kind of the symbol to represent this is you have one input and two outputs, and they're open strings. So you think of it as this with three punctures, or something like that. If you're used to symplectic field theory or something. Okay, another operation you might do, you might want to consider is well, this would be so-called an equivariant level. So I'm going to say, if you have some S1 action on the space, and even if it's not free, you could still form this quotient, which officially would be something of this form, some sort of Borel construction. But if you don't know that, that's fine to just think about it as a quotient. So I'm thinking of the closed loop space. you could form some sort of, take two loops, and construct a 2-to-1 operation where you look where they intersect and then you kind of join them together with some sort of resolution. Something like this. And that sort of operation might be characterized by a thrice punctured sphere or something. And this one, in the case of the equivariant theory, where you're kind of ignoring the base point or dividing out by the S1 action, this is called a bracket because it satisfies some sort of Jacobian identity. Is this visible down here? Or in general, you might like go hog wild and define some sort of like M to N operation with some sort of genus G and kind of look at some surfaces like this, and you kind of want to you actually look at some sort of moduli space of these surfaces, and you may even compactify it and define all sorts of operations. There's a whole bunch of these theories floating around. Okay, so this is kind of the idea. These surfaces tell you how to intersect your inputs and outputs in some sense. And they're not really maps in the pseudo-holomorphic way that you might think. But actually, in some sense, they could be almost considered some sort of constant maps.
So is the result a sum of the loops or a product of this?
This one right here?
Yeah.
This would be a product.
Product.
Yeah. I mean, it's not, you can't really call it a product, it's not necessarily associated with it. You're working over some algebra, some tensor algebra, symmetric algebra. Anyway, I'm not actually going to talk about this one. This is just kind of where people go with this. Okay, and so what are the issues when you try to define, and all of this kind of has a kind of general language called string topology. So what are the issues when you try to define some string topology theory? Well, the first one's kind of the best one. So what sort of algebraic structure do you get? So this the kind of the paper that started this theory by Moyer, Chess, and then Sullivan, they looked at this setup. They had a bracket, 2 to 1, a co-bracket, 1 to 2, kind of like this, but a equivariant version. And they proved that the bracket and the co-bracket were compatible in 2 different ways. It ended up being called an embodied Lie algebra. That was the structure in that case. So that's kind of an enjoyable exercise. Okay, now we're talking about intersections here, transversality. So, in order to get things well defined, you have to deal with this issue, like in symplectic geometry, where your transversality is the section Khobar and the 0 section. So are those intersecting transverse? You have a kind of more simple or finite dimensional question, but it's still not necessarily an easy question. And so is the intersection transverse? And there are a number of ways to approach this. Ultimately, probably the perhaps easiest way is to find some sort of sufficiently large set of strings for which transversality holds. And sufficiently large means it captures the homology of the strings, and you get well-defined operations on homology. That's one approach. Another approach, which is kind of can be more appreciated, but it's harder, is you want to get these operations defined on the chain level. And so then you might want to incorporate some sort of Euler, Kuranishi type argument, Kuranishi structures. And generally leads to infinity structures at the chain level, as opposed to kind of something like a co-bracket bracket. Anyway, so these are some issues you have to deal with at some level. So this one possibility. This is not the one I'm going to do. Okay, now here is kind of another version of well-defined, and this is kind of an important one. Another issue about defining these operations is, does the operation commute with the topological boundary? Okay, you need that in order for your operations to pass to homology, which is where ultimately you're going to start computing things. And for example, this one doesn't, because you can imagine if you had like a one chain of strings in some appropriate, or big enough chains such that you could see a one chain of locus, a locus of one chain of intersections where one of these loops is getting smaller. And you can quickly check that you're going to get something in this commutator, the operation that commutes the boundary. So that doesn't pass to homology. So that's actually a pretty lethal problem, and you have to deal with that. So, for example, in the original paper I mentioned, what they do is they actually mod up by constant loops and get both on there. Okay, and then finally, this is a question that Dennis Sullivan would care about, but probably a lot of people in the audience would care about. Is it interesting? That is non-trivial. And in what sense is it interesting? This is the kind of issue I want to talk about. So there's this open-ended question: is string topology a homotopy invariant or homeomorphism invariant, or maybe even diffeomorphism invariant? So the relative question that I want to address is supposing you have K as a knot inside R3, and you form some sort of string topology using open strings, are you going to pick up any non-trivial knot invariants? Because there's no homotopy theory of knots, all knots are homotopic. Okay. And there's kind of two schools about this. About which one that is. So I'm going to sidestep that question, and instead what I'm going to do is I'm going to introduce a sort of string topology which has some differential topology in it. So I'm going to look at strings that are transverse to the knot. So there, it's quite plausible that it's not a homotopy invariant, and indeed, we'll show that it's not. So the theorem that I want to describe is that we're going to consider space of open strings transverse to a knot K in R3, and I'll describe what I mean by exactly what I mean by transverse, because actually some more conditions than that. By the way, this transversality this making it transverse changes the space of strings. I'm removing a codimension 2 set, like this string. It's not in my space. Okay, and so I've changed the homotopy type of my space. So I'm in a new space now. This is unlike people know string topology. They choose some sort of sufficiently large set which has the same homotopy type of your space string. Okay, so we're going to define operations on this. On the homology of this space, and we're going to call this transverse open string topology, which recover so the first part is joint with all four of us. The Khobar algebra, and it's actually not the full frame invariant. It's setting lambda equals to 1, so I have to fill in the coefficients. I don't know what that is. which is equal to the Legendrian contact homology of LK, which none of these terms I'm going to describe, even though they're perhaps the most interesting to people here. So this is the degree 0. So this is degree 0 part of Legendrian contact homology of, okay, probably can't read this, but conormal lift, Legendrian conormal lift, LK, of the knot K. Okay. Now, this is not in a very direct way, though, this recovery, but we'll get to that in a bit. And then another application using this transverse string topology, and this is joined with Dennis, is that it also recovers, this is probably not as fancy invariant, but it covers the JSJ decomposition of the knot complement. So at least it's a non-trivial non-invariant. So the goal of this talk is to describe really what is this space in operations, how does it recover it, and
So you probably mean the JSJ S3
S3 because finite volume. Yeah. Okay. Okay. All right. So let me make some remarks about this before I actually go into the definitions. Okay. So the first one I kind of already said, I guess. So I'll just write it down. The transversality condition makes it a priori a diffeomorphism invariant, or it's a homeomorphism invariant. So it's not totally surprising that you should be able to, that you're not going to get a homotopy invariant. And in fact, there's another result by Basu who shows that he uses kind of a variation, slightly different, a different version of transverse open string topology to prove two homotopic lens spaces are not homeomorphic. This variation of open string topology we could also use, but in some sense it has a better definition, but the algebraic structure is a little more complicated. So, anyways, one or the other. There's another related result. So McGibbon uses another variation, which actually recovers all of LCH, not just the degree 0 part. Although he does need more inputs than we do. He needs to know what the group ring, the group is of the knot complement. So he gets more, but he uses more. And then finally, okay, this, right. So there is already connections between various flavors of string topology and symplectic field theory. It's a long list of names, but probably won't get down. So like Abu Zaid, Sullivan, right, Lachef, Zaido, Gaia, other people, who kind of construct some sort of very nice geometric, some sort of morphism, maybe sometimes even an isomorphism, from some sort of floor theory to string topology. So this is in symplectic geometry, and this is in differential topology. But as far as I know, it's not clear, at least talking about that any of these string topologies will be more than homotopy invariants. So kind of one kind of totally open question, I have no idea, is so what would be, you know, what does this transverse condition, what do they lift to in this sense of the symplectic geometry line? So that's kind of a completely open question in the sense that it's not even really a formulated question yet. And then let me just make one more remark. If K is a kind of transverse or Legendrian knot in standard contact structure, well, in whatever, in some transverse Legendrian knot, one could refine this transverse open string topology to include that information, to make the strings, let's see, transverse I want it to be parallel, or transverse to the contact distribution. And then, you know, I don't know what the right Latin word is, but a postus priori. It's a transverse or Legendrian non-invariant, of course, isn't interesting to be computed to have anything to do with any of the transverse non. No idea. Kind of like a secret hope would be, you know, this one's related to Legendrian contact homology, then maybe there's some relation to, you know, one of these, like for example, filtered Legendrian contact homology, but you really, this sort of proof has to go through the chord algebra or something, as far as I know. No connections there for transverse or Legendrian knots. Anyway, okay. All right. So we 11 bet clocks, right? So. All right, let's see some definitions. Okay. Two. Okay, so here's the setup that I want to consider. So first I'm going to define the space of strings. So again, we have a knot. Yeah, I've been writing it in R3, but maybe I do need. Okay, so we have a smooth knot. Now we're going to fix some data here. We're going to fix the point on K. We're going to fix a tubular neighborhood. Okay. And we're going to fix two sections on K. Two sections of the two frames or whatever. Well, one actually, one will be opposite. Such that kind of two antipodal sections. Okay, and so we're going to look at this sort of string space, this open string space, which I'll call ST. So we're going to look at smooth maps into R3, starting and ending on the image of these sections. and moreover, which pass through the tubular neighborhood linearly. Intersection n equals the union of lines of the form gamma. For some reason I wrote gamma minus to gamma plus. Okay, so let's see. So what do I mean by that? So I've got my knot, and okay, and let's say here's gamma minus is on the bottom. Gamma minus is on the bottom, gamma plus is on the top. And basically, I start at gamma minus, and then I hit, if I remember to go through the knot again, I'm going to go through in this linear manner, and then end at so here's the intersection of the knot. Okay. All right. And I'm going to stratify this space. By counting the number of intersections. And then there's one other space I want to consider that'll be useful, especially for the second result. So we're going to kind of consider some closing up of this. So given a string in this space, we'll define, I'll just denote a twiddle here, which basically what it does is it just takes this start point and closes it up. Now, this requires some choices, but because I have a point P, and because this string is not oriented, there's kind of up to some sort of homotopy equivalence canonical choice of doing this.
You go the way that doesn't hit P? Avoids P or the way?
Yeah, right. So maybe I should have said that. So I'm kind of avoiding P. Yeah, and actually, yeah, I should have said that. That's important. I have no strings that start and end on P, so it's kind of retractable. So, all right.
So P is on the knot or on the boundary?
P is on the knot, and my section is only defined over an interval. So here's P here, for example. And so I'm only looking at strings that, that start and end, and I guess it's also built into here. They also don't intersect P. They just intersect in this retractable interval. This is exactly the point where I could avoid and use, but I pay for that algebraically because I'm not going to have a well-defined product anymore. There is a result by Basu who actually can drop this condition and has a kind of studies partially defined operations, some sort of category of bimodules. And certainly the first unit could be repeated for all of this, dropping that, but don't really know why to do that. Okay, but anyway, so I have this closing up operation, and so we get another homeomorphic stratification. We'll tell the note, this is the space of closed up strings, and I can also stratify it. And I'll just put tildes everywhere. Okay. All right, so that's my space. Now to talk about the rest of the topology, I need to find some operations on it. Okay, so first of all, there's going to be two different products. Let's say I have some knot, which is, sorry, string, which is comes here, and then I have another string here. So this is gamma minus, gamma plus. But they don't match. I can concatenate them in two different ways. Going around this way, or going around that way. So we'll say this is gamma 1, and this is gamma 2. I can define gamma 1, gamma and gamma prime, gamma and gamma prime. I can define gamma, compose gamma 1 prime using one direction, and gamma compose gamma prime using the other direction. And I get two associative products this way. Okay. Another operation is a kind of splitting operation. Which will lead to a coproduct. And in this setup, I have that might go through. So I can find some, for each intersection, I can split the string at that intersection, and that will give me an operation from this strata to this strata. So notice I lose one of my intersections, so like this might be 1, 2. This is gamma, and this is end in the start. This would be gamma cut here for gamma 2, sorry, delta 2 of gamma. Okay. A couple more operations I want to introduce. I'll call these space maps, because they're going to be used to construct some sort of simplicial complex, not simplicial set actually. So there's two of them, and they go from STN to STN minus 1. They reduce the number of intersections by 1, and it's a pretty straightforward picture. So again, I have my knot in here, and I have a string coming through, intersecting, and I can kind of you've heard Jason talk about this. He calls this the resolution operator. I can come down that way or that way. This is the I intersection. And that was called D1I. D1I. 2I. I also have what I'll call a degeneracy map. Again, this is motivated by the role they play in the simplicial set we describe later. So the letters for that are SI1 and SI2, and they increase the number of intersection points. In the situation there, what I do is if I have a string, again, coming here, what I'll do is I'll just add a little half loop. So we'll come down, go along the boundary of the end, come back down. So that is either half a loop this way or half a loop that way at the ith intersection. And then the last one that I want to introduce is kind of a familiar string topology operation. It's an interior intersection. Of strings. Well, of strings, yeah. And here, away from the knot, so the knot's down here, I might have two strings which intersect, and I'll just do the picture that I drew earlier. Now this one is only going to be defined part on the appropriately large transverse set, but it'll be enough. All of these will be enough to define things at the level that I want them to. Okay, so first just a couple, just a remark or so. Because the transverse decay condition implies that everything commutes with the topological boundary, so that gets sort of the problem that I mentioned before, this kind of intersection point running off to the string, the end of the string. Another one that's pretty straightforward is that kind of all operations satisfy the appropriate relations that you want to impose. None of them are very surprising. It's basically just, each of these relations you want to just say you can reverse the order of things. First you cut it here, then you join it there, et cetera, et cetera. And so you've got things commuting, things squaring to 0, and so on. Okay, so, all right. So let me get to the easier thing to say about how to, the first statement, how to recover the word algebra. So how to recover this symplectic invariant. So we're going to define the product, I'll call it this, to be the sum of the two ways of resolving this string. So remember that was going around this way and going around that way. These things don't match. And we'll define the coproduct to just be the sum, kind of signed sum of splitting these things. I think I still have that picture over there. Okay. And we're going to look at a chain complex. So we're going to go straight to the chain complex instead of a simplicial set in this case. So we're going to look at the strings, and our boundary map will just be the topological boundary. So again, for those not familiar with this, and then if we look at this chain complex, and we sort of kind of like twist the differential by R, by give it this coproduct structure, based on this fact that everything squares to 0 nicely and commutes and so on. This is a differential graded coalgebra. So here we're using all the strings, and we construct a differential graded coalgebra. And then what we want to do to that, so it's kind of weird, you know, we want to get the chord algebra, which I haven't described what it is, but it's essentially strings which don't intersect the knot. Okay, it's homotopy class of those things. That's what Leonard uses to define chord algebra, which is eventually part of the contact homology. So what we're going to do is we're going to go the other way. We now have strings that intersect the knot arbitrarily a number of times, but in a transverse manner. And we're going to kind of make it an even bigger object. We're going to take the so-called Khobar construction. So this is an algebraic construction which kind of models, it's supposed to model some constructions from taking loop spaces, base loop space of a space. We use the same notation. So what is that? So let me just write it down, kind of without going too much into detail. Basically, I take my coalgebra. I'm going to augment it. You don't really have to know too much what that means. Just kind of killing one thing. I'm going to do a shift and grading. Then I'm going to take the tensor algebra of that. Okay, so that's very big now. It's tensor algebra of these strings that intersect, so kind of like multi-strings. And then this trick between going between coalgebras and algebras and back again is you take the original differential and you incorporate the coproduct structure into the differential. That's what the Khobar construction does. And then you give it a new algebraic structure, a new product structure. This would just be the formal tensor algebra. Okay, this is a DGA. This is a differential graded algebra. And the theorem then is that, two things. This differential graded algebra is actually related to the group rank of the complement. Yeah, so I guess here I am talking about R3. Okay, so this differential graded algebra is quasi-isomorphic or homotopy equivalent to what's known as what I'll call the twisted group ring. Know it this way, twist. So I take the fundamental group of the complement of the knot, I take the group ring, and then I twist, I twist the product. So normally without this, you have a product given by concatenation of elements of the group. But what I'm going to do where the product x times y is actually x ey plus x my, where this is concatenation. E is the identity, and m is the gradient. And essentially, it's supposed to, this E and this M, it's not too surprising, it's supposed to come from this fact here that when we're taking the product, we're going to run one way or the other way. One you can think of as E, and the other one you can think of as M. But there are differences in M. So kind of the more surprising thing about this is that, you start with something big and you end up with something small. I mean, with just the group ring, just these things. Okay, and then the second point is just kind of a reformulation, that if you take this group ring, which has, the not information in it, you add a formal identity. By the way, there's no more identity up here, turns out. Maybe it's the end, obviously. But anyway, this E is no longer the identity of this operation. Okay. So you add an identity. You just add the identity of some element in there, which multiplied by anything gives back the thing. And then you quotient out by something. So this has the not information. This has kind of no information. This is just a local thing. You take the same construction, but now you just look at this tubular neighborhood around the knot. Pi 1 of the tubular neighborhood removes the knot. And you also have the identity. Now I don't want to quotient by that. I want to quotient by the things it commutes with. So the commutator of that, the numerator. And this thing is the Yang output. So that's just a kind of a reformulation of it. So in some sense, it recovers a string topology because you're recovers the numerator, and the denominator is something to do with the knot. It's kind of like what to do with extra variables. Okay. And like I said, assuming kind of a lot of people know what the main chord operator is, to me that's a bad thing. So rather than saying, we're defining it, I should just say, first of all, that this invariant is possibly a complete invariant. It's the version, like I said, where you set lambda equals to 1, so it's not necessarily enough to cover the Alexander polynomial, but it's still far from being trivial. Okay. So, move on to the last part. We're covering the JSJ decomposition. So the idea behind here, because I'm not going to get to describe why it's true, is essentially what we're going to do is we're going to use the open string topology of the knot, or some version of it with these operations, to recover this closed string topology of the complement. And then we're going to use a result that says the closed string topology of the complement recovers this decomposition. And the key theorem going from open string topology to closed string topology is, people, there happens to be anyone who knows this, is some results by Goodwill and Bergalia, who kind of compare Hochschild homology of base loops with homology of free loop space. So that's kind of what's going on in the background. We can use that and improve it to show that it carries string topology operations. Okay, so let me just try to describe what version of open string topology we're going to use here. I did all the operations already. Okay, so first, so now we're going to go back to these closed versions of strings. So recall that I have this decomposition where gamma is the closed up version. So even though geometrically it looks like a closed string, it has all the information of an open string. Just added this formal kind of final loop connecting the start and the end. So it's still a sort of, it's an open string topology theory. Okay, so we're going to define some sort of cyclic structure. So we're going to define a map from STN to STN, which permutes by 1 the ordering of intersections. So this came from an open string, so it has an absolute ordering of these intersections. And I'm going to be sketchy here. I'm going to say we're going to look at some equivariant version of this. So that means a subset that is invariant under tau. I'm not really allowed to say that. And unfortunately, the only thing I am allowed to say uses the word category. So I don't know if that was one of the 7 words that you couldn't use. But let me just try it, see what happens. Trapdoor.
The other 6.
Okay, so this goes back to several people, Siegel, Milner, and Kahns. I mean, different, different points. Construction. And what they do is combine, that is, not like individually, but combine, what they do is that they show that they construct what's known as a cyclic model of a space, a cyclic simplicial model of a space. It's kind of an algebraic version of what a simplex would be for a space. And so, using their kind of ideas, there exists some sort of cyclic, simplicial model. And the standard notation is to put the space that you want to model algebraically in terms of, use the same letter, put quotes in it. Seems like that's the beginning of the literature. So I'm going to model this space of ST. Sorry. So again, essentially what I'm doing is I'm taking, there's kind of 2 ways of going. If you start with some sort of algebraic model, you can get a space, known as a geometric realization. And essentially what you're doing is you're putting in cells everywhere the model says to put simplices, and you're gluing the cells together everywhere, according to whatever the face map and degeneracy map works is telling you to do. So it's kind of, it has all that information. Okay, so essentially I've got some objects, which are STN, whose elements are n simplices of ST. And then I've got morphisms, where they're basically face map, degeneracy map, and this permutation cyclic map. So I'll use I'm just going to pick one of them now, STI. So remember there, I don't know if you remember this, but there was kind of 2 ways to do degeneracy maps, 2 ways to do face maps. So I'll just have to pick one, which can be done canonically. I mean, coherently. So these are called degeneracy map morphisms, face map morphisms, and cyclic map morphism. And they satisfy all the appropriate relations. And so on this space, I have a permutation well defined. And why? I should say that kind of all the when you do these models and constructions, you're kind of preserving all the homotopy equivalent, all the homotopy information, in particular homology and so on. So you could use your face map morphisms to define boundary maps and compute homology, and you will get the homology within the blank space. So if that's where you're going with this space, you're not really losing anything. Okay, and so we're going to let, so now I can say what this is. We're going to let this equivariant space be the geometric realization of the tau n invariant simplicial submodel, I guess, subset of this. So this I am allowed to say. And again, what I'm trying to get here is I don't have an S1 action on my space of open strings, but I'm going to get a cyclic action, which kind of models this S1 action I don't have. And this is going to be enough for me. Okay. So I've got 5 minutes. Let me do one more definition, concept definition, and then I can get to the theorem. Okay, so now, so that's the open string side. So let X be the not complement. And let me define the equivariant loop space really quickly. So Lx is the traditional notation for the free loop space. That is massive S1, massive S1 into X. And now, like I said, we have this, I forgot if I mentioned this at the beginning, but there's this thing called the equivariant loop space, which you're morally supposed to think of as Lx mod S1, where you have this S1 action on the domain, so you can precompose by that, and then mod out by that, and you get this space. But unfortunately, this action is not free. For example, constant loops remain constant, the same loop when you mod out. So you can't really do this. So what you really have to do is, use what's known as a Borel construction, which says you take so ES is the so-called contractible space. This kind of the unique up to homotopy equivalence contractible principal S1 bundle. And S1 we have acting by conjugation here by the left here, and it turns out that we get free action that way. And then we can take homology of this and call it the equivariant homology of this, or the homology of that. That's how you get around this. And somehow kind of you haven't lost any homotopy, you haven't changed the homotopy story. Okay. So Lx, this space has this bracket that I described earlier. And so the theorem is that, the main theorem is the theorem that we prove, and then the result is the one that I quoted, the corollary, is that there is an isomorphism from the homology of the equivariant loop space to the homology of these equivariant open strings that preserves enough information for us. The information is decomposition of H1 of the space given by components, right? If I have direct sum decomposition. If I have any space, I could have direct sum decomposition of its H1 in terms of its components. So there's that. And more important, and it preserves that, preserves the cyclic structure. And it preserves the bracket. So this result is an older result. Well, okay, not exactly, because we don't talk about this. We talk about it a related to this. So it's related to an old result by Vergele and Goodwilling. Unfortunately, I don't really understand their papers, but you can kind of improve it to this space. It's probably going to be the same isomorsism and then compare it on this level. And I'm basically out of time. So let me just say that there is another theorem by Moira Chas and Siddhartha Gadgil. We say that in general, for any three manifold, the JSJ decomposition of any three manifold is determined by exactly this. It's determined by exactly these dots above, namely this decomposition of any three manifold M. Components like this and bracket. So if you just apply this and this together, you get that the JSJ decomposition of the knot. And for those who don't know what the JSJ decomposition is, I'll just say at the very least, you can say, for example, the knot's hyperbolic. In that case, the JSJ decomposition is just one hyperbolic piece and no ciphered fiber pieces. Okay, so I'll end it there.
Are there any questions?
So you get information about the pieces in the JSJ decomposition as well as the way they're glued together?
Only if that they're hyperbolic or ciphered fiber and how they're glued together, but you don't know which ciphered fiber pieces they are. They're not. No. As far as I know, they don't know.